Hello, in this video we'll be talking about logarithms. And before we do anything, it will be wise for us to establish the relationship between indices and logarithms. So imagine that we have this expression 2 to the power of 3 equals 8. Now we can express this as a logarithm. And to express this as a logarithm, all we have to do is log. The base of our indices here is 2, so we're in a base of 2. And then the answer to our indices here is 8. So the question we're asking ourselves is, to what power do we have to raise 2 to produce 8? To what power do you have to raise the base 2 to produce 8? And that is 3. And so what we're saying is, if you have an expression, the base a raised to power n equals x, this can be expressed in logarithms as the logarithm to the base of a of x is equal to n. To what power do we have to raise a to produce x? As we have seen here, we have to raise a to the power of n to produce x. So the answer we have is n. And so this also tells us that if you have the expression on the right hand side, which is logarithm of a, logarithm to the base a of x equals n, to convert this back to indices, all you have to do is take your base and raise it to this power. So you raise this to this, and what you have is that x is equal to a raised to the power of n. And this is the relationship between indices and logarithm. So like I said, if you have an indices which is a base raised to the power of n, which produces x, you can express that in logarithm terms by saying that the logarithm to the base of a produces x, and then what you say is, what power do you have to raise a to produce x? And this shows us that you have to raise a to the power of n to give x. So you have to raise a to the power of n to produce x. Raise a to the power of n to produce x. So let's look at these simple ones that we have here. And the first one says the log to the base 3 of 9. What is the logarithm to the base 3 of 9? So remember, we're asking ourselves, to what power do we have to raise this base? To what power do we have to raise 3 to produce 9? And you know that 3 times 3 equals 9. So you have to raise, this is equal to 3 raised to the power 2. So you have to raise 3 to the power of 2 to produce 9. So the answer here is 2. The next one says log to the base 5 of 125. So you're asking yourself, to what power do I have to raise 5 to produce 125? And we know that 5 times 5 is 25, and 25 times 5 is equal to 125. So 5 raised to the power 3 equals 125. So we have to raise 5 to the power of 3 to produce 125. So the answer here is 3. The next question says log to the base 8 of 64. So the question is, to what power do we have to raise 8 to produce 64? And we know that 8 raised to the power 2 is equal to 64. So the answer here is 2. Log to the base 6 of 1296. To what power do we have to raise 6 to produce 1296? So we know that 6 times 6 is 36. We know that 36 times 6 is 216, and 216 times 6 is 1296. So you have to raise 6 to the power of 4 to produce 1296, and so the answer here is 4. So the simple, don't forget, just spell it out to yourself. To what power do you have to raise this base to produce this log, the number whose logarithm you're looking for, and that is your answer. So if we shake things up a little bit, here we know that we're seeking the number to which we must raise 4 to produce x. But here we want to seek x. And so what we're saying essentially is if we raise 4 to this power, we know this is always the power. So if we raise the base to this power of 3, what does that produce? 4 times 4 is 16, and 16 times 4 is 64. So x in this case, we can take this out and replace this by 64. So log to the base 4 of 64 is 3. The next question says log to the base of x of 729 is equal to 3. So we're looking for x here. Now the question is, so if we write this out as we taught ourselves, we know that the base is x is what we're looking for. And we know that we've raised this up to the power of 3. And this has produced 729. So we're asking ourselves, what do we have to raise to the power of 3 to produce 729? What do we have to raise to the power of 3 to produce 729? And if you look for the cube root of 729, you'd actually find that 9 is your answer. Because 9 times 9 is 81, and 81 times 9 is equal to 729. So we can replace this with 9. Log to the base 2 of 256. We're saying to what power do we have to raise 2 to produce 256? And if you use your calculator, or if you know this already, you know that you have to raise 2 to the power of 8 to produce 256. Log to the base 3 of 3. To what power do we have to raise 3 to get 3? That's fairly simple. That's 1. If you raise 3 to the power of 1, you produce 3 all the time. So this is 1. And so we'll be writing down our first law kind of. And that law says that if you have log to the base a of a, this is always equal to 1 regardless of what a is. If a is a positive number greater than 0, you always have 1. So let's keep this. We'll come back to this later. So if we follow this, log to the base 8 of 8 is if the base and the number whose logarithm we're looking for is the same, as in this case, log to the base 8 of 8 is 1. Log to the base 64 of 64 is 1. So this one says log to the base 8 of 1. What power do we have to raise 8 to produce 1? If you're familiar with the laws of indices, you know that anything raised to power 0 would always produce 1. So which means that we have to raise 8 to the power of 0 to produce 1. And so the answer to this is 0. And this brings us to another law which says that log to the base a of 1 is equal to 0. As far as a is a positive non-zero number, log to the base a of 1 is equal to 0. And so if we go to that by that, log to the base of 24 of 1 is equal to 0. You guessed it. Log to the base 10 of 1 is equal to 0. This one says log to the base of 25 of 5. So we're seeking to what power do we have to raise 25 to produce 5? And if you look at this and you see the relationship between 25 and 5, you would notice that 25 is the square root of 5, which means that we have to raise 25 to the power of half to produce 5. So 25 raised to the power half, which we know stands for the square root of 25, is equal to 5. So the answer here is half. The next one says, to what power do we have to raise 8 to produce 2? 8 raised to the power x is equal to 2. And you can tell already that we have to find the cube root of 8, which is raise 8 to the power of 1 over 3 to produce 2. So the answer here is 1 over 3. Now, before I go on, let me just point out what you may have missed here. You would notice that in the other cases, the base is always smaller than the number whose logarithm we're looking for. But in this case, the base is bigger than the number whose logarithm we're finding. And so if you have a situation where for logarithm to the base a of x equals n, if a is greater than x, then n is likely to be a fraction. As we are seeing in this case, 25 is greater than 5, so n, which is our result, is likely to be a fraction, which is 1 over 2. 8 is greater than 2, which in this case also yields a fraction, 1 over 3. So if we continue here, to what power do we have to raise 81 to produce 3? And you would notice that 81 raised to power x to produce 3. And x has to be 1 over 4. So 81 raised to the power of 1 over 4 is what produces 3. So our answer here is 1 over 4. To what power do we have to raise 16 to produce 4? You know that 4 is the square root of 16, so that's going to be half. So like we said, 16 is greater than 4. The base is greater than the number whose logarithm we're looking for. So our answer is most likely going to be a fraction. Now, log to the base of 216 of 6. You have to raise 216 to the power of 1 over 3 to produce 6. And so this is 1 over 3. So don't forget, if you have a logarithm where you have the base greater than the number whose logarithm you're looking for, then your answer is likely to be a fraction. Okay, this one says log to the base 3 of 1 over 27. So we're asking ourselves, to what power do we have to raise 3 to produce 1 over 27? If we break down 1 over 27, you'll see that this is 1 over 27 itself is 3 raised to power 3. And we know that if you know the laws of indices, please check my last video for that. You'll notice that 1 over 3 is equal to 3 raised to power minus 3. So we have to raise 3 to the power of minus 3 to produce 1 over 27. So this is equal to minus 3. So if we do the same for this, to what power do we have to raise 2, which is the base here, to produce 1 over 32? 32 equals 2 raised to power 5. And we know that this is equal to 2 raised to power minus 5. So we have to raise 2 to the power of minus 5 to produce 1 over 32. And this is equal to minus 5. And so if you notice here, the number whose logarithm we're looking for are fractions in these two cases. And for those, we've produced a negative number. So for log to the base of a of x equals n, if x is equal to fraction, then n is likely to be negative. So if you have a fraction, if you're looking for the logarithm of a fraction, and then your answer is likely to be negative. If we continue with this, to what power do we have to raise 5 to get 1 over 25? I think an easy way to do it, as you can see now, is just ask yourself, to what power do you have to raise 5 to get 125? And in this case, that's 3. And just add a negative number in front of that. So that's minus 3. Like in this case, to what power do we have to raise 2 to get 32? That's 5. Add a negative number, and that's what we have here. The same thing goes here. To what power do we have to raise 7 to get 2,401? That's 4. And because we have 1 over 2,401, which is a fraction, we know that this is going to be a negative. So that's minus 4. So let's move on. So we've done something like this before where we said log to the base 4 of 64 equals 3 because we have to raise 4 to the power of 3 to produce 64. Now what do we, if we have this, log to the base of 64 of 4. Now because we know that the base is greater than the number here, we're going to get a fraction. But what power do we have to raise 64 to get 4? We know that 4 is the cube root of 64, so we have to raise 64 to the power of 1 over 3 to get 4. And that is equal to 1 over 3. Now if you look at these two expressions, you would see a relationship. And that relationship is that on this side we have log to the base a of x, where a is equal to 4 and x is equal to 64. And on this side we have log to the base x equals a, because a is 4 here, a is 4 here, and x is 64 here, x is 64 here. So if you have this exchange of base and number in this case, what happens? And you can tell that in this case, this is n. If this is n, excuse me, if this is n, then this is equal to 1 over n. So if we write that out, what we're saying essentially is that log to the base a of x is equal to 1 over log to the base x of a. So if we switch the places of the base and the number, all you have to do is find the inverse of the results that you get and you're cool. So if we express that here, we know that log to the base 3 of 9 is equal to 2. So without doing any form of computation, we know that log to the base 9 of 3 is the inverse of this, which is 1 over 2. We know that log to the base 5 of 125 is equal to 3. And log to the base 125 of 5 is simply 1 over 3. Okay, we've also done this before where log to the base 3 of 27 is simply equal to 3. So we have to raise 3 to the base, we have to raise 3 to the power of 3 to get 27. So if we have this, because the number here is a fraction, we know we're going to get a negative number. But what negative number is it? So what power do we have to raise 3 to get 27? That's 3, like as we've expressed here. And because this is a fraction, we're going to have minus 3. So again, if you look at these two expressions, you should see a relationship. And that relationship is that log to the base a of x is what we have in this case, where 3 is equal to a and 27 is equal to x. And in this case, what we have is log to the base a still, but in this case, we have 1 over x. And from the answers here, you can tell that if you have this expression, then this is a negative. So log to the base of a of x is equal to minus log to the base of a of 1 over x. So if we go ahead and solve these ones that we have here, log to the base 2 of 32 is equal to 5. And so log to the base 2 of 1 over 32 is the same base, but there's an inverse. This is 1 over 32 in this case. And if we go by this law, you would see that this is 1 minus 5. Because if you raise 2 to the power of minus 5, what you have is 1 over 2 raised to the power 5. And what you have, 2 raised to the power 5 is equal to 32. Log to the base 5 of 125 is 3. And log to the base 5 of 1 over 25 is simply equal to minus 3. Take note, the bases are the same. The only things that change is the number. And the second case here is an inverse of the original number. So all you have to do is add a minus. And that's what you have here. So in this case, if we have that log to the base x of 1 over zq is equal to 3, then what is log to the base x of zq? It's an inverse. It's the same thing. All we have to do is add a minus, and that's it. Okay, so log to the base 5 of 0. What is this? To what power do we have to raise 5 to get 0? Now, if you raise 5 to the power of 0, you get what? 1. If you raise 5 to the power of 1, you get 5. Obviously, if you raise 5 to the power of anything greater than 1, which is like 2, you get something greater than 5, which tends away from 0. So that definitely no positive number satisfies this logarithm. What about negative numbers? If we raise 5 to the power of minus 1, what we have is 1 over 5. If you raise 5 to the power of minus 2, what you have is 1 over 25. So it's also looking like no negative number satisfies this logarithm. And so you can tell that it looks like the solution to this logarithm does not exist. And that's exactly what it is. Now the second one we have down here is log to the base 3 of minus 9. Now we know that if we raise 3 to the power of 2, we'll get 9. But this is not just 9, this is minus 9. And I can tell you that this is the same for this particular expression here. We cannot express the solution of log to the base of 3 of a negative number as a real number. So we can as well say it does not exist. So you cannot find the logarithm of 0, neither can you find the logarithm of a negative number. So if we do a summary of what we've learned, we're saying that if for an expression log to the base a of x is equal to n, if x is less than 0, so if x is negative, then like what we just said, the solution n cannot be expressed as a real number, so it does not exist. Now if x is between 0 and 1, which is a fraction, if x is a fraction, what said that n is likely going to be a negative number. And if x is 1, logarithm of 1 to any base is equal to 0. And for n is greater than 1, for x is greater than 1, then n is a positive real number. I think I missed out one, which is that if x is equal to 0 and then n does not exist as well. So if x is less than 0, which is negative, n does not, there's no solution for it. If x is between 0 and 1, which means it's a fraction, your n is likely going to be a negative number. If x is equal to 1, your n is always going to be 0. If n is greater than 1, which is a normal number, and then n is going to be a positive real number, and if x is equal to 0, then n does not exist as well. So the next thing we'll be looking at are common logarithms and natural logarithms. Common logarithms are just logarithms that are set to the base of 10, as in this case. So log to the base of 10 of 100 is simply the same as the logarithms that we've been finding before, which is, to what power do we have to raise 10 to get 100? And that is 2. 10 raised to power 2 is 100. To what power do we have to raise 10 to get 10,000? That is 4. All you have to do is count the zeros after the 1. To what power do we have to raise 10 to get 1 million? 6 zeros, 6. And in this case, to what power do we have to raise 10 to get 0.01? Don't let this scare you. This is simply 1 over 100. And we know that when we have a fraction, when we have the number as a fraction, we're likely going to have a negative number. So to what power do we have to raise 10 to get 1 over 100? And that's minus 2. All you have to do is count the number of decimal places and you get your minus 2. And you get your value here, then just add a minus to it. So in this case, to what power do we have to raise 10 to get 0.001? And this is also the same as saying 1 over 10,000, sorry. 1 over 10,000. And like I said, just count the number of decimal places, which is 1, 2, 3, 4, and you have 4. But because you know this is a fraction, you have minus there. So that's it. For natural logarithms are logarithms to the base of e. So if you have log to the base of e of x, what you can write this as saying ln of x. And there's nothing special about this per se in terms of how you handle the solutions. The only thing you have to know is that e is equal to 2.71828. You can continue writing this to whatever values you want, but we usually stop at something like this, 2.71828. So if you ever have to explicitly solve for e, you can replace e with 2.71828 at any point in time and you'll be good. All the laws that we've discussed before applies to both of these logarithms as well. The only reason these two are very common is because base 10, our number system is a decimal system, so it's only natural that 10 is also the most common logarithm. And e somehow is a kind of pattern that occurs a lot in nature, and because of that, e is also very common. So no fears. All you have to do is treat both logarithms like you would treat any other logarithm in any other base. So let's look at the laws of logarithm. The first one says that log to the base a of x multiplied by y is equal to log to the base a of x plus log to the base a of y. So if you have a product, if you're looking for the logarithm to the base a of a product, what you have to do is split that product and add both of them individually. To understand that, let's look at these questions. And the first one says log to the base 5 of pq. And so following this law, what we would have is log to the base 5 of p plus log to the base 5 of q. The next one says log to the base 6 of 54. Just like we can use this law to split up logarithms like this, we can also go back in the other direction. So we can go in either directions, either this way or this way. So in this case, we're required to go in the other direction. So we're required to contract this expression. So this is going to be equal to log to the base 6. Make sure that your base are the same before you do that, 6 and 6. Log to the base 6 of 54 multiplied by 4. And this is equal to log to the base 6 of 216, which we know is equal to 3. This one says log to the base k of a over b plus log to the base k of b over a. If we apply the law here, what we have is log to the base k of a over b multiplied by b over a. And b can cancel out b and a can cancel out a. And we would have log to the base k of 1. And we know that the logarithm to any base of 1 is equal to 0. So our answer here is 0. The next law we'll be looking at says that log to the base a of x over y is equal to log to the base a of x minus log to the base a of y. The first one we looked at dealt with product. In this case, there's a quotient. So if we have a division, if we're looking for the logarithm of a division, we can split that up by subtracting the individual of the numbers dividing themselves. So if we look at these examples like we've done for the previous one, here we have log to the base 2 of 40 minus log to the base 2 of 5. And so this is the same as saying log to the base 2 of 40 over 5, which is equal to log to the base 2 of 8. And we know that this is equal to 3. So that's that. And in this case, we can expand our expression by saying log to the base 5 of p minus log to the base 5 of q. And in this case, we can say log to the base e of 62 minus log to the base e of 13, which we know is equal to ln 62 minus ln 13. So ln 62 ln 62 is equal to 4.127, and ln 13 is equal to 2.565. And so the final answer for this is 4.127 minus 2.565. This is 1.562. That's it. The next law we'll be looking at says that log to the base a of x raised to power b is equal to b multiplied by log to the base a of x. So essentially what this is saying is that if you have log to the base a x raised to power b, all you have to do is transfer your b to the front of your logarithm, and you would have b multiplied by log to the base a of x. So like we did for the others, let's look at some examples. In this case, we have log to the base e of 2 raised to power x. Don't forget, when you have this situation, just move your x to the front here, and you have x log to the base e of 2. This is equal to x ln 2, which is equal to ln 2 is 0.693, so you can have 0.693x. For this one, log to the base 3 of 27 raised to power half. Don't forget, all we have to do is move this to the front, and we have 1/2 log to the base 3 of 27. We know that log to the base 3 of 27 is equal to 3. So this is 1/2 multiplied by 3, and this is equal to 3/2. For log q raised to power x minus n, something I forgot to mention when we were looking at common logarithms to the base 10 is that when no base is given, your logarithm is in base 10. If no base is expressed, so you can, for this where we don't have any base, we know that our base is in base 10. So this is simply, we move this to the front as well, and we'll have x minus n log q, and that's it. The next law says that if we have a raised to the power of log to the base a of x, this is equal to x. So if you have a raised to log to the base a, if this and the power of the base of the logarithm of the power is the same, this essentially can cancel out this, and you have x as your answer. So to understand that, let's do some examples. And here we have 5 is raised to the power of log to the base 5 of 2. The base here and the base here are the same, so these two can cancel out, and we can write our answer simply as 2. In this case, we have to get rid of this 3 first, and by so doing, we'll use the previous law, which is that, remember the previous law that says that if we have log to the base a of x raised to power b, we have b log to the base a of x. So in this case, we can go from here to here. So we'll move 3 up here, and what we'll have is e ln 2 raised to power 3. Now don't forget that e ln is simply e log to the base e of 2 raised to power 3. And from what we've seen, we know that this can cancel out this to give us 2 raised to power 3. And that is 8. That's it. So if we do the same thing here, we'll move up 2. We'll get rid of our 2 here, move it here as a power. So we have 7 raised to the power of log to the base 7 of x squared. And 7 can cancel out log to the base of 7 here because it is raised to the power. And our answer is equal to x squared. For the final one, we have 2e raised to the power 3 ln x. And we can rewrite this as 2 multiplied by, if we move this 3 over to the power here of x, we can write that straightforward as e raised to the power ln x cubed. And we know that ln is log to the base of e, so that means that we can cancel these two out to make this part of the expression x cubed. And so our answer is going to be 2 multiplied by x cubed, which is equal to 2x cubed. And that's our answer. So if we do a quick summary of all the laws that we've learnt, the first one is that log to the base a of x, y is equal to log to the base a of x plus log to the base a of y. The second one says that log to the base a of x over y is equal to log to the base a of x minus log to the base a of y. The third one says that if you have log to the base a of x raised to power b, this is equal to b log to the base a of x. The fourth one says that if we have a raised to power log to the base a of x, then this is simply equal to x. Now, to the ones that we've seen before, we know that if we have log to the base a of b, this is the same as saying 1 over log to the base b of a. And we also know that if we have log to the base a of x, this is the same as saying minus log a, log to the base a of 1 over x. And for the final two, we have that log to any base of 1 is equal to 0, and log to the base a of a is equal to 1. So we have 1, 2, 3, 4, 5. We have about 8 laws that, most of which are not really too complex to master, that if you can actually master these logarithms would help a lot in solving logarithm problems. The next thing we want to tackle is change of base. Now, if we have our expression log to the base a of x, we can actually change the base in which this logarithm is. And the simple expression with which we can change that is log to any base c of x over log to any base c of a. So what we're doing in this case is we want to change from base a to any base c. So we can do that by finding the log to the new base of x and dividing it by the log to the new base of a. So log to the base a of x is equal to log to any new base c of x divided by log to that new base c of a. So let's solve some examples just to be sure that we're conversant with this. We have log to the base of 3 over 4 of 25. When you have to solve a problem like this, the advisable thing to do is to convert it to either of the two bases that are most common, which is either to base 10 or to base e, because then you can evaluate that on your calculator. So in this case, you can change this to base 10 simply by saying log to base 10 of 25 here, 25 over log to base 10 of 3 over 4. And if you find the common log of 25, you would get log 25 is equal to 1.3979, and log 3 over 4, which is 0.75, because this is a fraction, expect a negative number. So you're going to have 0.75. Log 0.75 is minus 0.1249. And this is equal to minus 11.192. Log to the base of 32 of 16. We can convert this to, let's say, base 2 by saying log to the base 2 of 16 over log to the base 2 of 32. Don't forget, the first thing is the numerator is always the number and the denominator is the base. So we can convert it to any base we want as long as both bases are equal here, are the same here. So in this case, we can simply evaluate this by saying, so what power do we have to raise to get 16? We know that that is equal to 4. And so what power do we have to raise to get 35? We know that that is 5. To get 32, that's 5. So our answer is 4 over 5. The next one says log to the base 7 of 200. To solve this, let's use ln, log to the base e right now. So we can say ln of 200 over ln of 7. Now, ln 200 is equal to 5.298, and ln 7 is equal to 1.946. So this is equal to 2.7225, and that's the answer for that. The last one says log to the base of minus 7 200. So we can do this by saying, let's use the common log this time around, which is log 200 over log minus 7. This is actually a trick question because, as you would notice that we've said before, the logarithm of a negative number does not exist. So the solution to this question actually does not exist. And I hope that you had that in mind. It was just a trick question added there. So let's actually use all the things that we've learned in solving real logarithm problems. So the first thing we'll be looking at is the expansion of a logarithm expression. If we have log to the base 10 of this, we can expand this using the laws that we've learned. And we know, if I can just quickly remind you, we know that log to the base a of x, y is equal to log to the base a of x plus log to the base a of y. And we also know that log to the base b of x over y, there's no need to change that. So log to the base a of x over y is equal to log to the base a of x minus log to the base a of y. So in this case, for all the values that are at the top here, which is the numerator, they are multiplied values. So they are going to have, when we're doing an expansion, they will have the positive sign in front of them. And for the ones that are at the bottom, which are the denominators, they will have a negative sign in front. They will have negative signs in front of them. So if we expand that, we would have this to be log to the base of 10, 100, our first value, plus log to the base of 10, x squared, which is our second value. The third value is 9. It's a denominator, so it will have a negative, log to the base 10 of 9 minus log to the base 10 of y. But we're not done because we have a power here and would like to resolve everything. So this is going to be log to the base 10 of 100 plus, we move the power to the front here, which is going to be 2 log to the base 10 of x minus log to the base 10 of 9 minus log to the base 10 of y. Without using calculators, we can evaluate this to be equal to 2, because 10 raised to the power 2 is equal to 100 plus 2 log to the base 10 of x. We can't resolve this. Log to the base 10 of 9 minus log to the base 10 of y. Using calculators, you can evaluate this, but let's just leave it here. So let's tackle this, which is also to expand this. This is going to be equal to ln of the first value here, which is x, plus another value in the numerator, which is ln y raised to the power minus 3. For the denominator value, we'll have negative, which is minus ln e raised to the power 1.37. So we can further express this as ln x. Because we're bringing minus 3 to the front here, we would have plus minus 3 ln y minus 1.3. We're bringing this power down here as well. 1.3 ln e. Now this is going to be ln x plus times minus 3 is equal to minus 3 ln y. And we know that ln is equal to log to the base of e. And remember that we had said log to the base of a is equal to 1. So definitely log to the base of e is equal to 1. So this cancels out as 1. And then this is 1.37. And that is our final answer. So if we go on to the next one, we have log to the base 3. Our first expression here is x raised to the power 3. We have another expression in the numerator, so that's a positive sign, which is log to the base 3 of y squared. Then we go to the denominator, which is a negative sign of log to the base 3 of 27. Another expression in the denominator, negative, log to the base 3 of z raised to the power half. We can now bring down our powers. So we can rewrite this as 3 log 3x 2 log to the base 3 of y minus log to the base 3 of 27 minus half log to the base 3 of z. Looking through all this, the only one that we can express further is this. Log to the base 3 of 27, we know that to be 3. So our final answer will be 3 log to the base 3 of x plus 2 log to the base 3 of y minus 3 minus half log to the base 3 of z, and that's our final answer. So the next one says log to the base 5 of 125x cubed over 0.2y squared. So if we expand this, we have log to the base 5 of 125 plus log to the base 5 of x cubed. We move to the denominator, which is log to the base 5 of 0.2 minus log to the base 5 of y squared. Now we bring down our powers, and this is going to be log to the base 5 of 125 plus 3 log to the base 5 of x minus log to the base 5 of 0.2 minus 2 log to the base 5 of y. Now, we know that log to the base 5 of 125 is equal to 3 plus, we cannot evaluate this because we don't have a value for x, so log to the base 5 of x minus log to the base 5 of 0.2. 0.2 is actually 1 over 5. And this definitely we can say is 5 raised to the power 1. So this is equal to minus 1, and this is equal to 2 log to base 5 of y. Minus times minus in this case is going to be equal to plus, so we can rewrite this as plus 1. And that will be 4. This is 3 plus 1 here, 4 plus 3 log to the base 5 of x minus 2 log to the base 5 of y. Final answer. The next question says log to the base e of e cubed over x squared plus 4. So if we expand this, we would have that log to the base e of e cubed minus log to the base e of x squared plus 4. Now don't let this confuse you. E cubed over x 4 or 4x is not the same as e cubed over x plus 4. The law says that if there's a division, what we have is that the denominator and the numerator are subtracted. In this case, this is an addition, not a multiplication. So this is a whole expression. X squared plus 4 is together. So that's why we have this expression. So this is going to be rewritten as 3 log to the base e of e minus log to the base e x squared plus 4. And log to the base e of e is equal to 1. So this is 3 minus log to the base e of x squared plus 4. We can go no further than that. And that's our final answer. Let's move to the last question in expansion, then we'll move to contraction. Now, the first thing we'll have to do here is transfer the power to the front of our expression. And this is going to be 12 log x cubed y squared z raised to the power 5. And this can be rewritten as 12 into, so we can expand this as log x cubed plus log y squared plus log z raised to the power 5. And we can bring the powers to the front. So we can rewrite this as 12 3 log x plus 2 log y plus 5 log z. And then we can expand this finally by multiplying 12 by every expression here. And 12 times 3 is equal to 36 log x. 12 times 2 is 24 log y. And 12 times 5 is 60 log z. And that's our final answer. So just like we've been asked to expand logarithm expressions, we may also be asked to contract or condense logarithm expressions to have just one logarithm in our final answer. And we're using the same laws essentially. So for this particular case, all the numbers that have positives in front of them become numerators, and the ones that have negative become denominators. So first, let's get rid of this and make it a power here. So in this case, we're going the other way now. So we can write this as, we transfer 3 right here. When we're condensing, we go the other way. So this is equal to log to the base 2 of x cubed plus log to the base 2 of 30 plus log to the base 2 of y minus log to the base 2 of w. And then we can write our expression as log to the base 2. There's a positive sign here, so this goes to the top. There's a positive sign in front of this, so that is also added to the top 30. There's a positive sign here as well, so this is also y. And for this, there's a negative sign, so it goes to the denominator, and that's w. And so our final expression can be more accurately written as log to the base 2 of 30 x cubed y over w. And that's how you contract a logarithm expression. So for the next one, we have this, and we do the same thing by first transferring this to the power, and that is ln x squared minus ln y plus ln w raised to power a. And we can write our expression as, this is a positive sign, so it goes to the numerator, x squared. This is a negative sign, so it goes to the denominator, y, and this goes to the top here. And that's our final expression. The next one says log to the base 6 of x minus 2 log to the base 6 of y plus 3 log to the base 6 of e. And so this is equal to log 6 x minus log to the base 6 y squared plus log to the base 6 e cubed. And we can write down our final expression as log to the base 6 of x y squared, and there's a positive sign here, so e cubed goes to the top, and that's it. For this particular expression, we have that log to the base 7 of 10 multiplied by log to the base 10 of x squared minus log to the base 7 of y squared. If you had recalled that we had said that if we're doing a change of base, we have log to the base a of x is equal to log to the base c of x over log to the base c of a. We can rewrite this expression if we multiply both sides by log to the base c of a. We can rewrite this as saying log to the base c of a, which is this, multiplied by log to the base a of x equals log to the base c of x. If you look at this, if you take out this, what you have left is log to the base c of x, which is what you have on this side. So if you have this kind of expression where you have log to another base of a multiplied by log to a base a as well, then this can cancel out this for you to be left with this and this. So that's an example of what we have here. And I hope that is clear actually. If that is clear, then you can tell that because this is a log to the base of a, 10 can cancel out log to the base 10 here and leave us with log to the base 7 of x squared minus log to the base 7 of y squared. And then we can finally write our final expression as log to the base 7 of x squared over y squared. So just so that you have that again, if you have log to the base c of a multiplied by log to the base a of x, then this is equal to log to the base c of x. So this can cancel out this, and you're left with log to the base c of x. So moving on, we have log to the base c of x minus 2 log to the base 6 of y plus log to the base 6 of 4 multiplied by log to the base 4 of e. And I'm hoping that you can already see that this can cancel out this to make this log to the base 6 of e. And so if we start from the left hand side, we have log to the base 6 of x minus 2 log to the base 6 of y plus log to the base 6 of e. And then we can go ahead and rewrite this as log to the base 6 of x, move this to the power to form log to the base e of y squared plus log to the base 6 of e. And this is going to be finally log to the base 6 of x. There's a minus sign here, so y squared is going to the denominator, and there's a positive sign here, so this is going to be x e over y squared. And that's our final answer. And that's how you do contractions of logarithmic expressions. If we have an expression such as 3 raised to power x is equal to 11, this is not a very straightforward thing to solve. We don't know what power we must raise 3 to get 11. But we can solve this by taking the logarithm of both sides. If we take the logarithm of both sides, we can have log of 3 raised to power x is equal to the log of 11. And we can further write this by bringing x to the front of the expression here, which is x log 3. And this is equal to log 11. And because we're looking for the value of x, we can make x the subject of the formula here. So x is going to be, if we divide both sides by log 3, we would have log 3 cancels out log 3 here, and this is going to be log 11 over log 3. Using our calculator, we know that log 11 is equal to 1.04139, and log 3 is equal to 0.47712, and this is equal to 2.18267. You can actually confirm that by raising 3 to the power of 2.18267, and you should get 11. If we look at another example, here 6 raised to power x plus 3 is equal to 15. We can solve the same way by taking the log of both sides, which is log 6 raised to power x plus 3 is equal to log 15. Now we can rewrite this by bringing x plus 3 to the front of the expression here, which is x plus 3 log 6. And this is equal to log of 15. So to make x plus 3 the subject of the formula here, we can divide both sides by log 6. And that will be x plus 3 is equal to log 15 over log of 6, and we know that log of 15 1.176, and log 6 is equal to 0.778. So 1.176 divided by 0.778 is equal to 1.512. So x plus 3 is equal to 1.512, and x can then be equal to 1.512 minus 3 if we subtract 3 from both sides, and this is going to be equal to minus 1.488. Let's look at one more example. If we have e to the power of x minus 4 equals 12. Now, we don't always have to take the common log of both sides. In this case where we have a e, it could be more advisable to take the natural log of both sides, which is the ln. So if we have ln e raised to power x minus 4 equals ln 12. Now, this can be written as x minus 4 ln e equals ln 12. We know that ln e equals log to the base e, and this is equal to 1. So this becomes 1, and x minus 4 multiplied by 1 is x minus 4. This is equal to ln 12. We can easily express ln 12 using our calculator to get x minus 4 equals 2.485, which means that x is equal to 2.485 plus 4, and this is equal to 6.485, and that's our final answer. Let's move on to other things. To solve this particular equation, let's remind ourselves of the fact that if we have a raised to power n is equal to x, we had said that we can rewrite this as log to the base a of x is equal to n. So if you have a logarithm expression like this, to convert it back to indices, all you have to do is raise a to the power of n, and we'll be able to get our x. So if you have a logarithm expression, take the base, raise it to the power of the solution you have to get the number that whose log you're looking for. So if we do that here, it means that a in this case is 10. Our n is equal to 2. Our x is equal to 2x plus 50. So we can rewrite this by saying 10, which is our a, the base of 10 to the power of 2, to get our number here, which is 2x plus 50. So 10 raised to power 2 is equal to 2x plus 50. And this is equal to 100 equals 2x plus 50. And if we're making x the formula here, we'll subtract 50 from both sides. We have that 100 minus 50 is equal to 2x. This is equal to 50 equals 2x. And to get x, all we have to do is divide both sides by 2 to leave x here alone. And 50 divided by 2 is equal to 25. So x is equal to 25. We have log to the base 2 of x plus log to the base 2 of x minus 2 equals 3. So we can contract this because there's a positive sign here. We're going to use the law that says that log xy equals log x plus log y. So if we do that, we're going this way. And this is going to be equal to log to the base 2 of x multiplied by x minus 2. X multiplied by x minus 2. And this is equal to 3. So if we write this out, we'll have a log to the base 2 of, this is x squared minus 2x. If we expand that, 3. So we can have that, we would raise our base here to the power of 3 to get what is our expression here. So this is going to be equal to 2 raised to the power 3 is equal to x squared minus 2x. So if this is the case, this is going to be equal to x squared minus 2x equals 8. X squared minus 2x minus 8 equals 0. And we can recognize that this is a quadratic equation. Now we have to solve this quadratic equation if we want to find the values of x. So to solve this quadratic equation, we have to express this middle term 2 in terms of factors of 8. So the factors of 8 are 1, 2, 4, and 8. So which of these factors can we multiply to get 8? We can multiply 1 by 8 to get 8, and we can multiply 2 by 4 to get 8. So now that we know the pairs that we can multiply to get 8, how can we combine this and this or this and this to get minus 2. Now, from here you can tell that there's no way we can combine 1 and 8 to get minus 2. 1 plus 8 is 9. 1 minus 8 is 7. Minus 1 plus 8 is 7. 1 minus 8 is minus 7. So there is no way you can combine it. But you can actually combine these two to get minus 2. And that you can do by saying 2 minus 4. This is going to be result in minus 2. And so we're going to replace this minus 2 by this expression. And to do that, we're going to rewrite this expression by saying x squared, which is this. So this is going to be equal to plus 2x minus 4x minus 8 equals 0. So all we've done is split this up in terms of the factors of 8, which is, and this is the same thing actually, plus 2x minus 4x is still equal to minus 2. And then we factorize this. So to factorize this, the common factor between x squared and 2x is x. So this would be x. X squared divided by x is equal to x plus 2x divided by x is equal to 2. Then we have here the common factor between minus 4x and minus 8 is minus 4. So this is going to be minus 4. Minus 4x divided by minus 4 is x. And minus 8 divided by minus 4 is equal to plus 2 actually, equals 0. And so you can notice that the values in this bracket are the same and they're supposed to be the same. And so this is going to be equal to x minus 4, which is this and this, multiplied by x plus 2. This is equal to 0. Now, for this to be equal to 0, one of these have to be equal to 0. So x plus 2 either has to be equal to 0 or x minus 4 has to be equal to 0. And so we can say that if x minus 4 is equal to 0, then x is equal to 4. Or if x plus 2 is equal to 0, then x is equal to minus 2. So x is either equal to 4 or x is equal to minus 2. Now the problem with that is if we bring that here, so x is either equal to 4 or equal to minus 2. If you remember, we had said that we cannot find the solution for a logarithm of a negative number does not exist. So if that is the case, then x cannot be equal to minus 2 because minus 2 is a negative number and x has to be equal to 4. And so our answer is equal to x is equal to 4. The next question, to solve this, we can bring everything to this side and combine the logarithms to have just one log. And then we solve like we've done for the others. So if we do that, we'll have that log to the base 3 of 7 minus x. If we bring this over here, we have log to the base 3, 7 minus x minus log to the base 3, 1 minus x equals 1. So we can combine these two to give log to the base 3, 7 minus x. There's a negative sign, so it goes to the denominator 1 minus x. And this is equal to 1. So we do the same thing, raise 3 to the power of 1 to get what's in bracket here. So that's going to be equal to 7 minus x over 1 minus x is equal to 3 raised to the power 1, which is equal to 3. So if we do that, we can further solve this by saying that 7 minus x is equal to 3 multiplied by 1 minus x. We can get this expression just simply by multiplying both sides by 1 minus x. 1 minus x cancels out 1 minus x, and we have 3 multiplied by 1 minus x here. So this becomes 7 minus x equals, if we expand this, 3 times 1 is equal to 3, and 3 multiplied by minus x is equal to minus 3x. So we have to make x the shortest performance. If we subtract 7 from both sides and add 3x to both sides, let's just do that explicitly so it's not confusing. If we do that, we'll have that 7 minus x minus 7 plus 3x. So we're subtracting 7 from both sides because we want to move all the numbers here. And then we're adding 3x to both sides because we want to move this over here. So that's going to be 3 minus 3x minus 7 because we're subtracting 7 from both sides plus 3x. So 3x cancels 3x and we have 3 minus 7. 7 cancels 7 and we have minus x plus 3x. And this is equal to minus x plus 3x is equal to 2x. And this is 3 minus 7 is equal to minus 4. So there we have that x is equal to minus 4 over 2, which is equal to minus 2. And that's our final answer. For this next problem, remember the law that says that if we have a raised to the power of log to the base a of x, then this is equal to x. And that's the law we would apply here. Because if we can rewrite this by saying that 9 is equal to 3 raised to the power 2 to the power of log to the base 3 of x equals 4. Now we can move our 2 to the power here to form 3 log to the base 3 x squared equals 4. And then these can cancel out themselves. And so this expression is going to be equal to x squared equals 4. And to find x, all we have to do is find the square root of both sides. The square root of x squared is equal to x, and the square root of 4 is equal to 2. So x is equal to 2. So this next question says e to the power of 4 ln a plus half ln b. Now if we isolate this power for a minute, we would have 4 ln a plus half ln b. This we can rewrite as ln a raised to the power 4 plus ln b raised to the power half. And we can contract this such that we have ln a raised to the power 4 b raised to the power half. Now if we replace this entire power with this then becomes e to the power of ln a raised to the power 4 b raised to the power half. And because we know that these can cancel out this, our final answer is going to be a raised to the power 4 b raised to the power half. And that's it. And that's where we're going to stop this particular class on logarithms. And the next thing we'll be talking about are surds. And I hope you can join me for that video as well. Thank you for being here. Bye.